Welcome back, everyone. My name is Pedram, and this is where we do machine learning codes and concepts. Let's get started. All right, welcome back, everyone. This is module number 7, Logistic Regression, and we're doing the Python part. So let's go to the GitHub folder. So then machine learning USU. Well, actually, this is the account, right? And then you go to the machine learning USU GitHub folder, and then go to lectures and codes, module 7, logistic regression, Python. All right, so we can go ahead and either run it in Google Colab or on local computer. Well, actually for this one, no, because I did the previous two ones in Google Colab and I showed you how to run PyCaret in Google Colab or Scikit-Learn. Now let's do it in, I'm gonna do it in my local computer to just show you another example. All right, so you can go ahead and click connect and do it on Google Colab, but today I want to run this on my VS Code. So this is VS Code for those of you who are familiar. So you can, I install things through Anaconda, and then I have VS Code, and I install the relevant extensions, and it's ready to go. So if you're curious how to run things on VS Code, I have some videos on YouTube as well. You can check them out. All right, so this is the PyCaret already installed. So inside the PyCaret package, we can get access to the Scikit-Learn package as well. So I think, I created a separate environment for it. I call it PyCaret, and this is a full version of PyCaret. Okay, so we're gonna do both of them. We're gonna do logistic regression, just like previous modules. First, doing from scratch, coding kind of from scratch using Scikit-Learn package, and then we're gonna do automated version with PyCaret. All right, so logistic regression. We're gonna go ahead and import the relevant libraries, NumPy, Pandas, Matplotlib, Seaborn for visualization and ignoring the errors. And then set your random state is equal to 1000 if you want to see the exact same output that I see here. All right, so this is a data set that we're going to import, and here's the head of the data set. So this is a pretty simple data set that we're going to work with. And actually, this is the one that we talked about in the theory lectures, right? So we had two numerical features, right? Balance, this is the credit card balance at the end of the month, and then this is income. And we have a categorical variable, which is a student, if that borrower is a student or not. And then the target variable is going to be default, if they ended up defaulting or not, right? So there are going to be 10,000 observations. And I think for classification, the very important stuff, I think that's the most important first step, is to look at the balance of the data set in terms of your target variable, right? So our target variable is default, so I'm going to do a cross tab. Basically, I want to create something like this, and I want to count the number of no's and yeses, right? So if I have 2 classes, I'm going to see 2. If I have 3 classes, I will see 3 of them, right? Then I'm going to normalize it and then multiply it by 100 to make sure that these are percentage. So if I run this line, so I can see that 96% of the data, almost 97% of the data of the target variable is basically no default, and only 3% is default. So it seems that the target variable is highly imbalanced. And what do you think are the implications for performance metrics? If you have watched the theory lectures, you know that we cannot trust accuracy, or we cannot be super excited when we get a high area under the curve or AUC score. And why is that the case? Well, because that's actually goes back to the next question. What is the benchmark accuracy, common sense accuracy? So here, if I develop a model, a random model with no skills that can always predict no defaults, right? So what is the accuracy of that model? Yeah, 96.67%. So if I have a model that always predicts no defaults, so this is going to be the accuracy. So 97, almost 97%. So it's hard to beat this model. And this is our common sense accuracy. This is the benchmark. So if you run a model and you come up with a 96% accuracy, and you cannot even beat the benchmark. But the point is that when the data is highly imbalanced, we need to work with some other metrics like F1 score, like precision, like recall, like precision recall curve, and things like that, right? We're going to talk about all of them here, but a prerequisite for this Python notebook, understanding this video, is you have watched the theory lecture first. So I assume that you have already done so, or you're familiar with logistic regression and the performance metrics for classification, and now you're here. All right, so let's quickly check that if the data is clean, do some simple pre-processing. I'm gonna go ahead and make those categorical variables into dummies, right? Using pd.getDummies. So this is a getDummies method from the pandas data frame. We're gonna drop the first, and then we can rename the columns because by default, it's gonna generate something like default yes, student yes. We're gonna make it shorter. We're gonna say, if it is default yes, well, actually I can show it to you before renaming. So if I do df.head, so it's gonna say, yeah, default yes, student yes. So I'm gonna replace them with just default and students. If it is 1, it's yes. If it is 0, it's basically no. Right, so that's the data frame. This is the renamed version. And we can look at some summary statistics as well in terms of, I don't know, for example, the distribution of the continuous random variables and things like that, right? So now let's look into basically defining our features and target variable. Okay, so our y variable, the target is default, and the features are everything but the default. So we're going to have 3 features: balance, income, and students, right? One of them is categorical, the other ones are continuous. So we're going to do the pretty regular stuff, you know, from the Scikit-Learn model selection. We're going to import train test split, and we're going to split the data by 80% train and 20% test, and the random state is 1000. Okay. So if you use a random state 1000, you should see exact same numbers that I do here. So basically it means that this is your train set. The first one is observation number 5696 and etc. All right, cool. So we can look at the head of the train set as well. And now we are ready to basically build our first classification model, which is logistic regression. So I'm going to import a logistic regression class from linear model module, right, from Scikit-Learn. So let's go ahead and do that, and then we can get access to the data, get access to the model basically by calling logistic regression. So I'm creating this object. This is my model, and I'm going to use the plain vanilla version of logistic regression. How do I know that this is plain vanilla version? So let me go ahead and actually show you. So let me pull up the documentation. If I scroll down to the end of this notebook, the first link is going to take you to the documentation. I'm going to go back to that. Just bear with me for a second. So here, this is our model, right? So this is the model that we put together, right? So let's look at the documentation. So here's the Scikit-Learn documentation for logistic regression. So what are the parameters? So the first thing we have is called penalty, right? So for penalty, we can use L1, L2, ElasticNet, or none. So by default, it is using L2. So it means that by default, when you use logistic regression from Scikit-Learn, it is rich logistic regression. Remember those penalized regressions? So I think we talked about it on the slide as well. Let me see if I can pull up that slide quickly. This one, yeah. So by default, it's basically using this L2 and adding it to the logistic cost function and do the job for you. So we want to make sure that this model that we have is a plain vanilla version of logistic regression. So that's why I'm going to go ahead and change the penalty from the default to none. Okay, so no penalty is added. So yeah, we can talk about, well, let's actually talk about it here. What are other parameters? So we have penalty, dual, tolerance. So this is for convergence. This is important, C. This is inverse of regularization strength. Well, actually, it says that it likes SVM, so we haven't talked about SVM yet, but the smaller this value, it means that the stronger regularization, because that's the inverse of regularization strength. We can think of it as some sort of inverse of lambda, right? So here we have lambda. We said if lambda is bigger, it's putting more the restriction on penalization. So lambda is inversely related to C. So this means that if C is small, it means that we are penalizing the regression more, the logistic regression more, okay? All right, and then fit intercept, we have seen something like this for linear regression as well. And what else? Okay, we have class weight, right? So by default, all the observations are going to be equally weighted, which is pretty much just the case that most of the time we're gonna do it this way. However, we can go ahead, if the data set is imbalanced, we can go ahead and weight the observations inversely related to the frequency of observation. So what does it mean? It means that, for example, here we have 97% of the data no default, 3% default. So we can say because 97% is more frequently shown in the data, so we're going to give them less weight, give those observations less weight. And we are going to give more weights to the default observation, which is 3% of the data. So this is an option. We can do it that way, but I personally prefer to do it balanced or just leave it as none. And then instead of balancing the data like this, I prefer to report to use some other metrics for report. So for example, I do not trust accuracy now, but I can report F1. I can report precision or recall, right? So this depends on the task. You can try both and see which one fits your data better or fits your task better. Yeah, random state solver, again, these are computation stuff. And yeah, that's pretty much everything we need from logistic regression. And by the way, multi-class, right? So multi-class, so by default, what we're doing is binary classification here. We said if somebody's going to default on their credit card or not, right? So it's 2-class classification. But what if you have 3-class, 4-class classification? You don't need to be worried. You can just leave it as blank, and then automatically it's going to figure out how many classes you have, and then it's going to basically do 3-class classification, 4-class classification, right? And there are different methods, for example, one versus rest, and we're going to talk about them in the future lectures in the course. Okay, so how many output do you want to see? L1 ratio. I think you're pretty much familiar with this L1 ratio as well. If you're doing penalized logistic regression, and if L1 ratio, for example, is 50%, then this is going to be elasticnet, right? So 50% rich, 50% lasso. All right, I think that's pretty much it. And we can extract these things. We can extract coefficients, intercepts, number of features, and yeah, that's pretty much it. Okay. So let's go back to the code. Now that we are quite familiar with this logistic regression class and the parameters, we can play around with it. So we create an object, call it logistic, and off of that object, we are going to train the model using train sets. So we use a train set. Now the model has been trained. Now we can get access to the outputs, right? So the outputs that we see here are kind of interesting, right? Because there's going to be 2 outputs for us. One are the y-hats, and y-hats are directly coming from logistic predicts in the test set, right? So this is my model. If I say make prediction using test set, it's going to give me the y-hats. These y-hats are a bunch of 0, 1s, right? True, false in the binary case. In 3-class classifications can be 0, 1, 2, and etc., right? So this is, and by default, the logistic regression is using the threshold of 50%. It says that, okay, if the probability is greater than 50%, call it 1 or true. If the probability is less than 50%, call it 0 or false, right? So this is one kind of output we can get. Another one, as you can guess, are the probabilities, because probabilities are also useful, right? We can plot them, we can look at the distribution, and etc. So if you want to get access to that, you have to do logistic.predictProb. So this is a method that we're using, and then you have to pass the test set. And I'm extracting the first element. So first element is the probability of default. So let me show you what I mean by that. So if I do something like this, if I say, hey, from the logistic, just give me everything, round it up to 3 digits. It's going to be something like this. You see, because I have 2-class classification, I'm going to have 10,000 observations, predictions here. And then this is a probability of class 0, probability of class 1. So probability of default. What we are interested is this column, 0.001, 0, 0, and etc., right? And no surprise, this model is going to be most probably almost all the time predict that there's going to be no default. So that's why the probability of default is going to be small in many observations. Okay, so we're going to extract this second column, which is going to be by doing something like this. Now my y-hats are a bunch of 0, 1s. So let's look at, well, we can look at that one. These are the classes from our object that we trained, right? So the classes are 0, 1s. These are the y-hats. So as you can see, y-hats are a bunch of 0, 1s. So all for the first 10 observations, they're all 0. It means that no default. And but a more interesting thing is this y-hat probability. So I can look at the histogram plot, right? So this is the hist plot. Well, let's see. There we go. And let me see actually. Okay, sorry. And this is a histogram, right? So, and it seems that, yeah, the majority of the probabilities are less than 50%. So no wonder why the model is almost all the time predicting no default because, again, the data set is super imbalanced. We can look at the maximum number or maximum value of y-hat probability, just if you're curious. So we get a 96%. So there's an observation in the data. There's a person in the data that with 96.5% probability, he or she is going to default. So that's that one. And then we can also play around with something like this. So for example, say, hey, tell me how many of those probabilities are greater than 90%. Give it a sum. So it seems that only 4 observations out of 10,000 has the probability of default greater than 90%. Okay, let's move on to the discussing about these thresholds, right? Because we said that by default, the threshold is 50%. The model is going to call anything above 50% 1 and below that 0. But what if you want to play around with some other thresholds? So for example, 10%, 30%, 80%. So how do we do that? So for example, well, first of all, remember, your model is going to predict that all credit cards will no default and hence generating too many false negatives if you're doing 50% threshold, right? To avoid having too many false negatives, what can we do? We can reduce the thresholds, yes. To avoid having too many false positives, we're going to increase the threshold. So in this case, imagine we want to reduce the thresholds of false negatives, the number of false negatives. So we can play around with the threshold 10%, 30%. So a cool thing with that y-hat probability is that we can create 2 other target, well, let's say predictions off of that. We can say if the threshold is greater than 10%, call it 1, otherwise 0. So I'm going to call it y-hat 10. So these are the predictions that when the model predict anything above 10%, call it default. The same story for 30%. I can do something like this again, just for fun, let's call it. And then because it depends on the task that you're doing, you can play around with these thresholds, or we can use some metrics that are threshold agnostic, like AUC, ROC, and we're going to talk about those things down the road. All right, so now I'm going to go ahead and create a nice data frame. I call it DF predictions. These are all my predictions. So this is my actual value, and this is my probabilities, and this is probabilities using 50% threshold, and these are going to be the same. This one and this one already, because by default, logistic regression is using 50% probability. And then I have y-hat when 10% probability, y-hat 30% probability, right? So again, sorry, this is the probability. This is how we label them, 0, 1s, right? So let's go ahead and show that. Okay, so now we can see what the model is doing, right? These are the outputs of the model, the probabilities. Then how do we want to label them? That's subjective. If the threshold is 50%, these are the labels. If the threshold is 10%, these are the labels. If the threshold is 30%, these are the labels. And as you can see for this observation, because the model predicted that with 14% probability is going to default, that's why y-hat 10 is 1 and those 2 are 0. Okay, and then you might wonder, okay, how do I know that what is a better threshold? So again, there are 2 ways to approach a question like this. Once it depends on the nature of the task. So for example, you're doing some COVID test results. You want to absolutely avoid sending too many false negatives in the society. So you want to reduce the threshold. Or if you're doing some spam detection, you want to make sure that not everything goes to your spam folder. So you want to reduce that false positive. You want to say, okay, you know what? Just call them spam when you're 90% sure. So that's why you're going to increase the threshold to 90%. So that's one way to approach these tasks. Another way is that leave it by default, which is 50%, and then play around with the performance metrics, right? So report those ones that are threshold agnostics, or look at some plots that can give you some insight about what is the optimal threshold you should use. And we're going to talk about it in the rest of this video. All right, so let's go ahead and import the performance metrics from Scikit-Learn. So Scikit-Learn metrics, accuracy score, recall score, precision score, F1, Matthews correlation coefficients, and you name it. And hopefully you watched the theory lecture, where we covered all these stuff, right? So we talked about all these metrics, and hopefully you know what are they. And now we're gonna see how we can calculate them in Python. All right, we can go ahead and look at our classification report. And again, these are something we are going to use for visualization and the confusion matrix. Okay, So this classification report is a built-in function in Scikit-Learn that it gives you basically precision recall F1 for different classes, which is nice. Okay, let me go ahead and import this one. And we can look at a bunch of statistics, right? The first one is our confusion matrix. So let's look at the confusion matrix. So confusion matrix, you have to pass two values, the actuals and predictions. So remember, this y hat is the same as y underscore hat underscore 50s, because by default you're using the threshold 50, right? So and this is going to be a bunch of 0 1s. In the actual value, we have 0 1s, default or no. In predictions, we have 0 1s, default or not, right? So this is not informative if you see something like this. So what are these numbers? Which one is true positive? Which one is true negative? And then which one is false? So we know that we don't know if rows are predictions or columns are predictions. So in order to give you some idea, this is consistent with the output of, let me actually zoom in a little bit, you can see better, with the output of Scikit-Learn. Okay, so the rows are actuals and the columns are predictions, right? So this is going to be our true negative, this is going to be our true positive, this is going to be our false negative, and this is going to be our false positive, right? So these are the confusion matrices. And as you can see, we can go ahead and create our own confusion matrix output with better labeling. And this is what we're going to do down the road. Okay, another thing is this built-in classification report. So we can pass the classification report and we have to just, again, pass actuals versus predictions. This is a nice summary, right? So it's gonna give us a nice table like this. So let me interpret it for you pretty quickly. So we have two classes. If you have 3 classes, you're going to see 0, 1, 2. If you have 4 classes, you see 0, 1, 2, 3, right? So for binary classification, we can report some numbers. I can report, let me actually show you this one. Yeah. We can report, for example, precision for class 1, recall for class 1, which is this one. I can do precision for class 2 using these numbers. I can do recall for class 2, which are these numbers, if that makes sense, right? By 2, I mean 0, no default. Okay, and then, yeah, so we can report those numbers. So that's why what we see here. So this column, this row is something like this. Precision for class 0, the model is doing an awesome job. So for no defaults, the model is just getting it. Recall is even better. So actually, what was recall? For those that were actually no default, what percentage model picked it? What percentage model recalled? So 99%. So as you can see, for class no default, the model is doing a decent job. An F1 score is simply a harmonic mean between these two, right? Support, what is support? This is a number of observations for that class. So as you can see, it's highly imbalanced. So we have 2,000 observations here. And remember, this is a test set, so that's why the data was 10,000 and we split it 20% test, so that's where the 2,000 is coming from. So off of that 2,000, 1944 is class 0. And again, we can read these numbers like that too. But when it comes to class default, the model is start having a hard time, right? So for example, what is precision? The precision is that the ones that model actually labeled them as defaults, only 66% of them in reality were default, right? What is recall? Recall is something like this. Among those that in reality they were default, what percentage model was able to pick? Only 34%. So as you can see, models having hard time picking up the default class. And then F1 is a harmonic mean, and it's going to tell you that it's only 45% based on using 56 observations. Then we can look at the accuracy. So accuracy is for all classes. So that's why we see one number here. It's 98%. You might be super excited with this. Okay, 98% is awesome, but you have to be very careful. Number one, your common sense benchmark was 97%. So you're doing okay. It's better than common sense, but you should not be super excited. 98% is relative to what? Relative to 97%, not relative to 70%, for example. And number two, the data is highly imbalanced, right? So when it's when that's the case, I will look into this number, not this number. And what are these things? So this is macro average, weighted average. So macro average is basically the average of, for example, this is for precision. precision for class 0 and 1. So simply I'm saying 98 plus 66 divided by 2. And then here I'm saying 99 plus 32 divided by 2, 67. And 99 plus 45 divided by 2, 72. Okay, so this is the macro average. Weighted average is weighted by the number of observations. So as you can see, we have 1944, I don't know, maybe 95-ish, or even more than that. 99% of the data is precision of 98%, and 56 observation precision of 66%. So if I do the weighted average, it's going to be very close to 98%. So that's why it's 97%. So 97%, 98%, 97%. So if your data set is imbalanced, I will look into this number, and that's it. So hope that that number is a large one. Okay, we can do Matthews correlation coefficient as well. So in order to just give you a reminder, what is Matthews correlation coefficient? So it's going to use all the numbers in the confusion matrix, and it's informative in terms of its magnitude and the sign. So it's positive, so it means that the model is just capturing some correct classification. It's not completely misclassification because it's positive, but the magnitude is not that, well, it's not bad, it's 46, but it's we know that the max is 100%. Okay. So now we saw a bunch of statistics using Scikit-Learn package, and then we can create our own function, right? So here's what I did. I created my own logistic report. So basically what we're doing is we want to make it more flexible, right? We want to say, hey, this is your threshold. By default, I'm going to use 50%. By default, this is a plain vanilla version of logistic regression. By default, you're not touching the class weights, right? And we have to just pass the train test, both features and target, and that's it. So it's going to create a model, train it, make predictions, and grab the first one for these are the probabilities. And then we can say if that probability is greater than a threshold, call it 1, otherwise 0. Okay. And then confusion matrix. So this is where we can make it a little more appealing in terms of visual, right? So we can say, hey, this is my confusion matrix, call it CM. And I can go ahead and calculate the accuracy, precision, recall using these functions from Scikit-Learn, right? So we have to pass actuals versus predictions. We are rounding up everything by 2. F1 score, MCC, the same story, but this is my labeled confusion matrix, right? I'm going to say, hey, this CM, which was a 2x2 matrix, what are the indices? The indices are actuals, negative, positive, and the columns are predictions, negative, positive, because I want to make it consistent with this, okay? Actuals as rows, indices, and predictions as columns. Okay, we want to create that output. And we can print out the accuracy, precision, recall, F1 score, MCC for class 1 or default here. So this is our very own function. Now, if I call that function and pass the values, I will see a nice report. So this is a nice report, right? So this is a lot more informative than what it comes as an output of confusion matrix in Scikit-Learn, right? So you can create your own version. So now we can play around with this, right? If I change the, for example, threshold to 0.1, what do you expect to see? I want you to pause the video and think about it. First of all, why would you want to reduce the threshold? Because you want to reduce the number of false negatives, right? If you do that, if you reduce the false negatives, so if you make this smaller, what will happen to the recall? The recall is going to get larger, right? Because remember, that thing is going to show up in the denominator, and then the whole thing is going to increase. Okay, so if I do that, I expect this number to decrease, number 1, this number increase, and then we can look at the overall F1 score, right? So let's do that, 1, 2, 3. Here you go. So our false negative decreased, the recall increased dramatically, but the F1 score in total, it decreased. So maybe threshold 0.1 is not a good number in terms of optimal threshold. So we're going to look into some plots at the end of this notebook, and then you'll see which one is going to tell you the optimal threshold, right? All right. So now, what is implication? So how can we use this function, or basically what is the implication of picking different thresholds? So I come up with a hypothetical scenario for you, and hopefully it's going to make it clear why we can play around with these things. Okay, so imagine, for For example, you're a lending company, right? How do you make money? So you're going to decide if you want a model, right? And that model should say, okay, if people are going to no default or default, right? So obviously, if your model says that you are you're not going to, well, you're going to default, you're not going to lend them money, right? And if the model says no default, so you're going to lend those people money. So basically, we're interested in this column. You might do this column, the ones that the model predict no default. So I'm going to lend these people 1934 plus 37 people, right? You might want to say that, hey, what about the opportunity cost of these guys? Because these were correct numbers. Well, you didn't lend them money anyways, right? So these are the ones that in reality, they defaulted and model picked them. And so you're more concerned about these guys. So there's going to be a cost associated with this and profit associated with this. So these are the people that didn't default and the model said no default. So you made money off of them. But these are the problematic ones, right? So these are the ones that the model predict no default, but in reality, they defaulted, right? So you're losing some money. So if you want to just define an objective function, profit function, it's going to be something like this. It's going to be your true negatives multiply some value. So this is your true negative. These are good numbers. And minus, because this is cost, false negatives multiply some other value. So we're going to give them some different values. And I'm going to say, let's magnify this cost by 4 times, right? So this is, imagine this is our objective function we want to optimize. So let's see. So what is the solution to this problem? So we're going to say that find a threshold that maximize this objective function. Hopefully it makes sense. Again, you're a lending company and you want to model basically, and you want to see what is the optimal value for threshold to maximize your profit. So usually it's something like this, you know, in a combination with another optimization problem that you have create your own thresholds, right? So yeah, here is the threshold of 0.5, just a reminder. I can go ahead, I have a nice, let's say function here. I can create my profit function as well. So let's say this is my profit function. Remember, we want to do something like this. Okay, so I need to get access to this confusion matrix first, and then true negatives, extract true negatives and false negatives, and then that's it, and create something like this. So I'm going to say this is my profit function. Pass me the train set, test set, threshold, and the value associated with true negatives, these ones. How much value these people are going to bring to your profit, and then the costs of these ones. So I'm going to call it VFN. So here, just for the sake of argument, we can assume that both of them are the same. But you can say, well, typically this is a lot larger than this, right? So for example, if it is 10, it can be 50, it can be 100, right? And the thing is that the number of these, let's say, these false negatives are going to be a lot smaller than true negatives, right? All right, so again, we're training a simple model and extracting a confusion matrix. And then these are the numbers we're interested. It's a 2x2 matrix. I'm interested in element 0, 0, so basically this, and element 1, 0, basically this. Okay, so 1, 0. All right, and this is your profit function. Tn multiply, true negative multiply the value you associated, and then the false negative multiply 4 times of the value you associated. Let's say 10 and 40, right? All right, so this is my function. Now I can play around with this, right? So this is going to be literally my profit, right? So I say this is a data, and then if threshold is 0.5, what is my profit? There you go, 17. Let's say these are 1,860. If I do the threshold 0.3, let's see if the profit increase or decrease. The profit increase, right? So obviously you don't want to just manually randomly search. You want to put it in a nice for loop and then go through different values of thresholds. So this is what we're doing. So imagine we go threshold 10% to 100% by incremental of 10%. And I'm going to do a list comprehension, doing my profit, everything. We're changing threshold for threshold in these numbers, 10% to 100%. That's it. We can create a nice table. So this is my table based on different thresholds and profits. We can visualize it, and obviously it's maximized here, maybe 0.3 something. We cannot see it visually. We are going to use argmax to extract that component. So this is a result data frame profit column, argmax of that column, use it as an index for this data frame. I can use index location or location, really doesn't matter. So both of them are going to give me the same numbers. So it seems that threshold 0.3, 30% was optimal with the maximum profit of 18,300. Well, yeah, 18,300, yeah. Okay, so hopefully that use case was informative, and then you are more excited about learning logistic regression and play around with those thresholds. All right. Now let's talk about the ROC AUC. Remember we said that, we already talked about all these things. Now the last one is this one, the ROC AUC. This is the one that, let me actually maximize it. So we talked about true positive rates versus false positive rates, and then you want to plot this. So for different thresholds, we're going to calculate true positive rate, false positive rate, and then we pick a number. And ideally, this is a perfect classifier, the purple one. And AUC is going to be 100%. And this dashed line is our random classifier or no skill classifier. So it's going to be, the area under the curve is going to be 50%. Anything between the two is acceptable. Anything below random classifier is nonsense. So we're not going to accept that one. And then hopefully we get as close as possible to the far top left. Okay, so let's create that one. So we're going to do it manually first. Don't worry about it. Honestly, don't worry about it, because down the road, I'm going to use PyCaret, and then PyCaret is going to do this exact same plot, even more informative, just using one line of code. But for those of you who are interested what we're doing, I added some comments here. Hopefully it's straightforward. What I'm doing is that this NS stands for no skill and LR stands for logistic regression, right? So what if you want to do no skill? The probabilities are going to be always 0. So this is a model that is always predicting no defaults. If it is always predicting no default, what is the probability of default? 0. So that's what I'm doing. Say 0 for everything. And then my logistic regression probabilities are basically, these are the one coming from the model, right? So these are the outputs of the model, right? And we are extracting the second column, which is the probability of default. And then the rest is just pretty straightforward. You're using some functions from Scikit-Learn. So the AUC for no skill, we're using this function. We have to pass actuals versus probabilities. Be careful, actuals versus probabilities. We can calculate AUC for no skill, AUC for logistic regression. We can print them out. So this is this part, right? And then we want to do plot. So for plot, let me actually run this. For plots, we are going to use ROC care function from Scikit-Learn, and we have to pass again the actuals versus probability. The output is going to be 3 things: false positive rate, true positive rate, and threshold. So we don't need thresholds for plotting purposes, so I'm going to just ignore it by doing some underscore. So the output is going to be false positive rate, true positive rate for no skills, false positive rate, true positive rate for logistic regression. Now I have these two, I can simply plot them, right? So this is literally your X and Y. I'm going to plot X, Y, so that's why we have false positive rate as X and true positive rate as Y. And then this is a style, color, and etc. So no skill is going to be this line, and this is what our model is doing, and AUC is 95.8%. Oh, here's an exercise. Again, pause the video before looking at the answer. Are you excited about this AUC? Why? Well, hopefully you get to this conclusion that not necessarily, because this data set is highly imbalanced. It means that the accuracy of the model just like a benchmark or the common sense is going to be super high. And this means that most probably, regardless of the threshold you pick, the AUC is going to be large, right? So we're not going to use that one. So we will use something else, like precision recall or a fun score. All right, now let's do cross-validation. So if you have watched the previous videos, we talked about regression models. We talked about the metrics for regression, which was, let's say, mean squared error, RMSE, R-squares, you name it, right? For classification, we have a lot more statistics to play around with, right? So I'm going to remind you of all those metrics. So from Scikit-Learn metrics, let's list the name of scorers. So this is it's a dictionary. We are extracting the keys. These are the values, right? Accuracies for classification. adjusted, well, let's look at F1 macro. So we're interested in these ones. For example, F1 for our task, which is highly imbalanced. We're going to pick that one. But you see, here's a list, F1 macro, F1 micro. Then we have our regular negative mean squared errors for regression as well. We have precision, we have recall, and all the macro micro versions. Now you know what is macro micro. We have ROC. We can do the cross validation, basically look at the metric of ROC and things like that, right? All right, so let's remind ourselves that what is our basic model. The basic model is plain vanilla version of logistic regression by setting penalties equal to none. And now I can say, hey, use this model as an estimator. This is my trained test set. Trained features and targets. And then based on that, do cross-validation for me. What do you want to report? Report the F1 score, and then do 5-fold. So I'm going to run this. It's going to do the cross-validation using trained set to get an estimate of the performance of the model in the test set. So I'm going to have 5 of these numbers, take the average, 0.36. So this 0.36, I can compare it to the F1 score in the test set that we reported up there. So I don't remember what was that number, but let's see, if you use threshold 0.5, so it's, this one. That's an estimate for this 0.45. Okay, so, all right, so this isn't a train set, but I have to do test set though. So I can do xtrain test, y test, well, actually y test in the test set. Well, sorry, my bad. So this is actually, it was reporting the performance in the test set anyways, so my bad. So yeah, this is an estimation of this 45%. Okay, cool. So that's the cross-validation kind of thing. And the very last thing I want to report, well, yeah, let's see what else we have. Yeah, so we can look at the, if you've trained something, for example, we have logistic, right? And the model has been trained, simple model. We can call .score, and by default in classification, .score is going to give us accuracy. In regression is going to give us our score. In classification is going to give us accuracy. So we train this model one more time, and then we'll calculate the score or accuracy in a test set, 97.6%. Are we excited? Not that much. We outbid the common sense model, which was 96.7%. But this per se, it's not a huge number, given the fact that if your model did nothing but predicting everything to be no defaults, it's doing slightly better. Okay, so this next part is just advanced visualization. And honestly, when we're doing PyCaret, this really doesn't matter. The reason that I'm doing it here is to make sure that we are able to replicate all this stuff, right? So I want to replicate this thing for you. Just right there, I'm going to show you. We talked about this last time. So we used 2 features, income and balance, and then we scaled the features. You see that the features are scaled. Look at the magnitudes. And then we came up with a formula for this line. This is our decision boundary, and I want to visualize it. Actually, this was generated by using the list code. Okay, but for practical purposes, don't worry at all. We're going to use PyCaret. PyCaret is going to do this job with 1 line of code. So I'm going to fly through this code here because this is pretty straightforward. So we're going to keep 2 of these just for visualization purposes. 2 of these columns, balance and income. So that's why I keep them. I train test split the data one more time. So here we are scaling the features. I'm importing standard scaler. And there you go. We are, again, training a model, making some predictions. We can look at the coefficients. So this is what we were talking about. So what are the coefficients? So if I go back here, so this is W1 is the coefficient of balance, W2 is the coefficient of income, and B is the intercept. So this is what we extract. W1, W2, intercept. There you go. Okay, now this is our line, right? So the line, our decision boundary is this. W1 balance, W2 income plus B. So 2.69 balance plus 0.22 income minus 6.06. So this is the line that we can plot. Again, don't worry about this code here. You can copy paste mine, or you can ask ChatGPT to generate it for you. I think nowadays creating plots like this is easier and easier, or you can use PyCaret. So this is the line, right? So this is our decision boundary, and this is a formula for that. 2.69 balance plus 0.22 income. So this is what we see. So if you set, for example, income is equal to 0, where are we? Here. And then solve for balance. So balance is going to be 6.06 divided by 2.69. It's going to be 2 point something. There you go. This is your 2 point something. And you can solve for income by setting balance is equal to 0. If balance is equal to 0, then the income is going to be 6.06 divided by 0.2020, so 30 something, 20 something. So it's going to go all the way up when it hits this y variable y30. So this is your classifier, decision boundary, and using train set. So I can go ahead and plot the same thing for the test set, and this is what you saw on the slide. All right, right? So the model is going to call everything on the left green, no default, everything on the right red, default, and the dots are the real observation. So for example, this is the real observation. This, no, these are the dots are. So for example, look at this one. This is the one that the model predicted 1, and it was actually 1. This is a good thing. This is what the model predicted 1, but it turns out to be green, so it's a false prediction, and etc. So we talked about these things and labeled them properly in the previous theory video. So check it out. All right, so and then one last cell here, just for fun, I put it all together. So I call it my logistic report, ROC. And if you go through this code, this is nothing but me putting everything together that we did in the previous cells, and then generated a nice output with the ROC. Again, this is just fancy stuff. You know, honestly, PyCaret is doing a better job than this. So I don't know. No, you can play around with it. You can do some Python programming exercise if you want to. I don't know. This is going to enhance your coding skills, let's say. You can play around with it. But at the end of the day, I have a nice function. I call it my logistic report ROC. I pass the train test set. I pass the threshold. It's going to give me this nice output. Give me the AOC. Give me the plot. Give me these metrics. Give me the confusion matrix, which is labeled. Okay, so all right, that was pretty much it. Doing things in Scikit-Learn. So now let's talk about the PyCaret. Okay, PyCaret installation. Again, by the time you're watching this video, I don't know, maybe things have changed, but right now the latest version is 3.1. So if you do if you're doing it in Google Colab, you have to do pip install PyCaret every single time you run the code, but or you open your Google Colab. But remember, this is my local computer. I'm running things on this environment, which is PyCaret. And then I already installed the full version. Actually, what you're seeing there is the full version of PyCaret on my computer. So when I pull up the model names, you're going to see it's going to be a couple of more models compared to what you can see in Google Colab. Okay, so we're going to import, let's say the version is 3.1, and then this is the same data set. Let's import it one more time. Look at the head of it. And then from PyCaret classification, let's import everything. Let me actually pull up the documentation just in case. So we're going to open this one and the code, the model container, because we're doing some tuning stuff, and then hopefully we can talk about it. So let's go to classification. And here, if I do logistic regression, there you go. So this is our logistic regression. And what are the tuning hyperparameters, by the way? There's not much to tune here, so let me remind you what we're doing. This is logistic regression, right? So there's literally not much to tune unless you want to do penalized logistic regression. If you want to do penalized, then you have to decide, okay, should I pick L2, L1, elastic net? And if that's the case, what is L1 ratio, right? So where's the L1 ratio? It was up there somewhere. Yeah, L1 ratio, right? Or what is the C value, right? The smaller, the more magnitude you're giving to penalization, right? So, or you can think of it this way: the smaller C, the larger lambdas, right? So maybe these are only the few hyperparameters that you can play around with, and the default values that PyCaret is using, I don't know. Let me see, what are those numbers? So, for example, yeah, for grid, for C is using a number between 0.001 to 10 by these increments. So this is decent. And then for L1 ratio, we should find those values somewhere here in the tuning part as well. Okay, so we have arguments C. And let's see if they play around with the L1. So probably they do somewhere. So, okay, cool. And let's go back and let's create our experiment. So the experiment is something like this. This is a data, I call it dfpy, so here, right? The target is default, session ID. Again, if you want to get the same answers as mine, use it. This is your random generator. Train set 70%, pre-processed true, and categorical features. So we remember we have this is another feature we have, and I'm going to tell PyCaret right away, this is categorical, okay? You don't need to decide, I'm telling you, this is categorical. You can set up the experiment, and then, so because the PyCaret thing is going to take a little longer, I'm just going to run through the code, okay? So I just hit run button here just once to make sure that things are working, and then everything else should work from your end as well, because I have run this before. Okay, so these are the models. So I'm going to give it some time. Okay, so it's pre-processed now. The experiment has been set up. Now we can call them models. We can create models and etc. So PyCaret is really nice in terms of visualization and then doing machine learning quickly, right? So for example, I can do models, and then these are the model IDs and etc. Be careful, this is classification. So LR is not linear regression. Because this is classification, it is logistic regression. So remember, we imported everything from the classification. Okay. So linear regression, KNN, decision trees, SVM, you name it. We're going to cover quite a few of these things down the road. We're going to talk about XGBoost, LightGBM, and etc. So if you do it in Google Colab and if you do pip install PyCaret, you're not going to see a couple of these models, including CatBoost. But if you install the full version, you're going to see all of them. So this is why I see CatBoost here as well. Okay, so you can go ahead and create your logistic regression by doing create model. We have done this before for linear regression as well. Pretty much the same syntax. And here's the documentation for you if you're interested. Again, very, very good extensive documentation it comes with. And actually, what I really like about the ChatGPT web browser thing is that, because if you use the default ChatGPT, it has been trained until September 2021, so it doesn't know the latest changes in PyCaret, right? But if you use the browser version of ChatGPT, or if you do Google Bard with the browser or Bing with the browser, any large language model with the browser connectivity, like Po.com, I think they're doing a web browser version as well. You can say, hey, this is the latest version of the documentation of, let's say, classification PyCaret. Use that link and then help me to write code in PyCaret. So it's gonna literally read through this entire documentation for you and help you build your model. So I highly encourage you to give it a try. It's worth it. And yeah, coding these days is becoming a lot easier and easier. So that's why I really want you to focus on the theory more and then be less obsessed with the coding one. But it doesn't mean that you should not learn how to code in Python. So that's a different topic that we can talk about it maybe at some point. All right, so this is my logistic regression. We're doing 10-fold. Did I specify 10-fold? So probably I did. Well, by default it's 10, so that's because I see 10 output here. So 10-fold classification, well, 10-fold cross-validation, so that's why we see 10 numbers here, and these are the average values. Accuracy, AUC, recall, precision, F1, kappa, and MCC. So kappa is something we didn't cover in the theory lecture. Basically, this is, it just want to make sure that it's just saying, hey, for example, these are, it's going to connect the predicted label to actual label, just like any other metric, but with the difference that it's going to take into account the odds of random, just chance, right? So is it by chance they're in the same category or not, right? So we usually stick to F1 if the data set is imbalanced. So our F1, 10-fold cross-validation, 27.69%. I'm going to go ahead and tune this model, right? So let's go ahead and tune this model with, if I do tune logistic regression, I'm going to use tune model function and then pass my trained or object, right? So it's going to go ahead and do that. It will take a little longer. And did we make any improvement? Yes, we went from 26% to 30%. And if you're curious what were the optimized parameters, you can say, hey, off of this tune logistic regression, give me the parameters. And these are the parameters. So the C was 3.77 again, it's not easy to read it because it's inversely related to your lambda and etc. You have to see what is your model is using. So your model is using L2, so this is rich. So it's using rich logistic regression with 1 over lambda is equal to 3.775. Yeah, I think, yeah, L1 ratio, yeah, because this is rich, L1 is basically none. Yeah, intercept fit true and etc. So this is the detailed tuned version of the model. Now you can use this tuned version and then use scikit-learn and create your own one, right? Using scikit-learn. Okay, so this is the part that I'm really excited about using PyCaret, right? So plotting things, I love the plotting components of PyCaret. So if you go to the documentation and go to plots, let's see, where is this? Models. What was it? Plot model? Am I missing something? Let's see. What are they? Yeah, plot model. Why do I not see plot? Let me just search my eyes. Yep, plot model. Okay. So these are the available plots for classification. I think we did the same thing for regression. So this is for classification. What can be plot in classification? There are tons of them, right? We can look at AUC, threshold, PR, which is precision recall. We're going to look at all these things, by the way. Confusion matrix, error. These are class report. This is kind of built-in classification report. We can look at the decision boundary. How beautiful is that, right? So remember, we use, I don't know, 20, 30 lines of code, and now it's 1 line of code. We can look at the learning curve. We are going to do that. We can do, yeah, we don't talk about validation curve. I think for the final project, I'll barely talk about it. We can do feature importance if it is I don't know, kind of decision tree based classification model, and etc., right? So let's keep things simple, and I'm going to add to this PyCaret component as we progress through the semester, right? So these are the relevant ones that we're plotting. You can plot the parameters. So this is pretty much the same as if you call the get parameters just method, right? We can do AUC. So what is this? This is what we created, but it is a lot more informative, right? So now I have 4 numbers instead of just 1. So the cool thing is that it's going to report for both classes. So the blue one is the ROC for class 0, no default. The green one is the ROC for class 1, default, and these are the area under the curve. And then we have micro average of those numbers as well. So remember, what was the micro average? So the macro average calculates the true positive rates, false positive rates separately, and then take the average, simple average. Micro average is going to take the weighted average based on the sample number of observations that were defaults or no defaults, right? So that's why the weighted average is going to be pretty close to, let's say, the AUC that we calculated before, because it was weighted by, so for example, one of them was 98% with 2,000, I don't know, almost 2,000 observations. The other one was a smaller number with only 50 observations. So the average is close to 90 something, 95 plus. So that's why this is 95, 99. Okay. Then we can do threshold. So this is very interesting, right? That we can look at this is a plot of precision recall F1, all these good stuff versus threshold, right? So if threshold is 0.2, these are the values. If threshold is 0.9, 0.8, these are the values. And you know that we already talked about it. The lower the threshold, the higher the recall. So this is our green thing. Green line. The higher the threshold, the higher the precision, right? Depending on the nature of the task, you can play around with those things. And then what is this vertical line? So this is here, in this case, it is 0.3. So, and this vertical line indicates an optimal threshold values that balance different metrics. So just keep in mind, maybe your magic number here is 0.3, right? It's going to give you a good balance of precision recall and F1. So this is great. And if you have no prior belief that what should be the threshold, and if you don't want to use 0.5, so maybe you can look at this plot and then decide. It's going to give you a balancing, right? But if your task is, you know what, I just want to focus on recall, so go ahead and pick the threshold that maximizes your recall. Okay. All right. So then we can look at precision recall plot, right? So this is also an interesting plot, which is useful, especially when your data set is highly imbalanced, right? So let me walk you through this. First of all, this is simply plotting precision numbers and recall numbers for different thresholds, just like this that we did true positive rate, false positive rate. Now we're doing precision recall for different thresholds, right? So this is, ideally, it should be something like this, right? You know, if it goes toward the top right, it's better, because why not? You want to have precision 1, recall 1. You want to be here, okay? And just like AUC, we can calculate the area under the curve. So the higher that number, the better. So those are the similarities between the two. But another interesting number that we can report with this precision recall curve is, it's called average precision. So it's 0.3 here. So what does it mean? It means that you can say your recall is between 0 and 1. And then for any values of recall between 0 and 1s, we're going to calculate the related components of precision and take an average of those numbers, right? So I don't know, I'm going to have, let's say we divide it into 1,000 numbers between 0 and 1. So I have 1,000 number for precision, and I use a simple average, and the average was 0.3. So this means that the average precision for the model is 0.3. So then this is a lot more informative than AUC here, right? So is this a good number? Well, I wish it was larger, but let's compare it with our benchmark, the common sense thing. What was the common sense? The common sense was that go ahead, common sense default, go ahead and predict everything is no default, right? So it's going to give you accuracy 97%. If everything is no default, so your model is not predicting, let me show you actually here. If the model is always predicting no default, so I'm going to get two numbers for true, negative, false, negative, and these things are going to be 0, right? If these things are 0, then your true positive rate and things are going to be 0 all the time, right? Or you can think of the precision is going to be 0 too. So because it's 0 divided by something. So then you're comparing an average precision of 30% to 0, well, which is a lot better. So your model, this model is better than a no-skill model. Right? So I'll take it. All right, so then we can have confusion matrix. So we have seen this before, but now the labels are hopefully a little more. Yeah, we have predictions and actuals. So this is good. This is good labeling. Then we can have the classification report. So precision recall F1 for different classes and support. So we have seen this before. And by the way, here I'm doing 30%. I wish I did 20%, which the answer was more consistent, but it is with what we did in Scikit-Learn. But here we are doing 30%. So that's why we have 3,000 observations for the test set. Okay. Then this is our nice decision boundary, right? And I would love this from PyCaret, because what if you have 10 features, 20 features, 30 features, right? And then you want to make sure that this is a principal component of feature 1, this is a principal component of feature 2. Don't worry about it. We're going to cover these things later on. But the idea is that the example that I gave you in class, or in the theory lecture, we assume that, let's say we have only 2 features, only balance and income, and this is the visualization we did. What if you had age, gender, education, etc., and then you still wanted to visualize it in 2 dimensions? So we have to go from that 10-dimensional space to lower dimensional space, let's say 2-dimensional space, using some techniques that we're going to learn them down the road, but PyCaret is going to do it for you anyways. So that's going to be cool. And this is what the decision boundary look like, right? And then lastly is our learning curve. So learning curve, if you remember, we have to look at the learning curve versus the score. Here's accuracy, and for train set versus cross-validation. If there is a huge gap, it means that the model is suffering from a model bias. It's not flexible enough. If the gap is shrinking, it's good news. But if there is more room for extra convergence, it means that, okay, you need more observations, more samples, right? In this case, they're converging pretty decently. So this is good news. So maybe my 6,000, 7,000 observation in the train set is okay. Actually 7,000. But it started increasing at some point, both of them in the train and cross validation. So I would love to see if we had more observations and it could increase the accuracy of the data. And I think in this case, that would be the case. All right, so that was the PyCaret part. So hopefully you enjoyed this tutorial. And then please make sure you double check the documentation of all these things at least once, right? So when you become an expert, you really don't need to look into the documentation, but at least as beginners, I highly encourage you to read through the entire documentation for logistic regression, Scikit-Learn, or PyCaret, and you name it. So some part of your time should be spent on these things. And I think I covered everything, but if there's anything haven't, I don't know, for example, if you need more explanation in basically talking about the micro, macro, weighted average of all those classification metrics, check out these links. But honestly, ChatGPT is doing a decent job when it comes to things like this. So try it out. So copy this thing and paste it in ChatGPT, say, hey, how can I interpret the results? Or if this was too fast or funky, you can say, hey, copy this line and paste it to ChatGPT, say, can you interpret the result for me? Again, cool. Thank you so much. And until the next one, take care.